Often, when forming a part, you'll be dealing with liquid material at one stage or another. Different plastics have different characteristics while molten. Depending on how thick it is, the harder it will be to completely pack into the mold. Think about trying to squeeze honey into your mold and what that honey would stick to. When I have the point of material introduction at one end of the model and only allow for one avenue of venting, this is an exaggeration of the problems you may find. A properly designed part has enough gaps, vents, and avenues for the molten plastic to flow into and fill the part completely. It's also helpful in a larger surface area part to fill from the center of volume and vent at the outermost extents of the model. Most importantly, it reduces built-in tension and stress as much as possible. Non-uniform filling and cooling can introduce stress. This can lead to your part warping out of shape or even cracking. I can't give advice for every project, but on a basic level, more friction in the mold equals more interior stresses. Friction can be introduced whenever the flow has to change direction, especially acute angles, or when your wall transitions are aggressive instead of incremental. Running simulations and working to eliminate material stress in the design phase is better than on-the-spot problem-solving later. On some plastic parts, you'll be able to see flow lines where there are visible waves following the path of the molten plastic as it fills and cools in the mold. When plastic is flowing from different directions, and these masses meet, you'll get something called a weld line, or a knit line. Some level of texture and the right amount of materials can emphasize or camouflage this mark of manufacture. Whether you're working with thermoplastics or thermosets, you'll have to beware of your worst enemy, bubbles. The bubbles I'm talking about aren't fun soap bubbles with low surface tension. They're tolerance-blasting, problematic voids. In prototype batches, bubbles can be introduced to both mold and casting material during mixing from the ambient air. Any bubbles in your mold will be present on every single cast. Bubbles in your casting material can disrupt clarity and leave ragged corners. Depending on your material choice, there are ways to mitigate these little dudes. In general, the longer curing time you have, the more time you have to work the problem before it sets. You can use that time to suction the bubbles out with vacuum chambers and shrink down the remainder in pressure pots. In any mold, bubbles can also form due to the surface tension of your corners, and you'll have trouble getting these acute sharps to fill in. Bubbles are voids and tend to stick to acute edges, corners of things, and also with gravity, float to the top. You should be doing material tests. And if you, for example, find that the half-inch top of your mold always fills with bubbles, work that into your design with funnels and vents. You can also add design elements, like sprues, above your part in the mold to be cut off later. Gas traps are usually due to inadequate venting. The air being displaced by the plastic has to go somewhere, ideally out of the mold. For example, two masses of material move toward each other, but there's nowhere for the pre-existing gas to escape to, so it gets trapped in the plastic. Watch out for voids along knit lines in tight areas or features that are too thin to fill in properly. This would be an example that has an inflow at one point of material introduction and has outflow in the middle of this figure 8. So you've got the draft required. You made sure your project is designed for manufacture, and you get your first run of parts in. Wait, did these get smaller? They did! Less exciting than it sounds, but when polymer parts cure or cool, they get smaller. And that rate of shrinkage depends on a couple of factors. Since polymers are long chains, think cooked spaghetti, they can have a grain direction, like wood. Even 3D prints have shrinkage. Just for kicks, some polymers will shrink at different rates along the axis of the grain than they do perpendicular to the grain. Different materials shrink at different rates, so pay close attention to the shrink rate when working with material suppliers. Other factors that can affect shrinkage have to do with how long the material is kept under pressure in the mold, the thickness of the part, temperature, flow rate, etc. If you aren't filling the part uniformly, or features of your parts are too thick, they can shrink at different rates. A part with a feature exceeding recommended thickness for the material may still be functional, but due to shrinkage will look oddly deflated. There's a whole science to predicting shrinkage, so do your homework and check with your manufacturer. In addition to dreaming about your voidless, non-stressed part, you should also consider the gravity of the situation. Gravity comes into play when your casting material is being introduced without external pressure. i.e. molding by hand. It's less important with pressurized mass production methods. If you're pouring material into the mold from the top, your mold will be subject to the force of gravity. Even the strongest of wills will still be subject to this force, so part of your mold design will require picking the best orientation of your project to the ground. Positioning helps aid my elephantine example. If it's integral to my design to have the parting line along the midplane of the elephant, this curling trunk is going to be a problem. If you can put the elephant on its side, these problems are solved. Because you're pouring down the material is going to have a very hard time traveling up and around corners like this. My solution to this would be to add more than one point of material introduction with plenty of vent toothpicks to trim off later. The principle works with pressurized molding too. It's hard to pack curly features like this when your injection site is too far away from it. Keep these gooey dynamics in mind by leaving your material enough outs and you'll be good to go.